Good day everyone and welcome to our next lesson. In this video, we will be focusing on the first part of our lecture on heat transfer by convection. On this part 1, we will be focusing on forced convection, while on part 2, we will be focusing on natural convection. Okay? With that, let's begin with a review of the modes of heat transfer. You have already been introduced to the heat transfer by conduction, and you were able to calculate the rate of heat transfer as well as the heat flux for heat transfer by conduction. In this lesson, we will be focusing on convection, or the transfer of heat associated with the movement of a fluid. Convection always relies on a fluid to transfer heat from a high temperature to a low temperature body. So you can expect in this lesson that we will be heavily focusing on liquids and gases. As I have mentioned, convection is a heat transfer mode primarily driven by fluid flow. Without fluid flow, there can be no convection. If for some magical reason we were able to restrict the movement of a fluid such as air and let it transfer heat without moving, then that would lead us back to conduction. Okay? It's no longer convection. Our rule of thumb in convection is the faster a fluid moves, the more it can transfer heat. Of course, this is limited by the identity of the fluid as well as the characteristics of the system itself. But this is more of a general guideline. There are two types of convection, natural or free convection, and forced or induced convection. Again, in this lesson, we will be focusing first on forced or induced convection. We have here the governing equation for heat transfer via convection. It looks familiar because we have already used it in the computation of resistances in our previous lesson. Okay? So we have the general equation, small q, or the rate of heat transfer by convection, is equal to HA times delta T, H being the heat transfer coefficient by convection. Okay? And if we rearrange this equation to fit the form rate is equal to driving force over resistance, we now see that the resistance due to convection is the term 1 over H times A. So do not forget our governing equation for convection. We will be using this equation a lot later. Okay? Next, let's first review our diffusivity. Back in our discussion in momentum transfer, we have the momentum diffusivity, which is symbolized here as nu, and that is equal to the absolute viscosity mu over the density rho. The momentum diffusivity will be important in our discussion today because, as I have mentioned earlier, momentum transfer plays a key role in convective heat transfer. Next, we have the thermal diffusivity that we have first encountered in our discussion on conduction. We have alpha is equal to K over rho times Cp. Since both diffusivities have the same dimensions, that is length squared over time, their ratio must be dimensionless, meaning the units will just cancel out. If we take the ratio of the momentum diffusivity and the thermal diffusivity, we get a dimensionless number that we call the Prandtl number. Prandtl number, when simplified, is equal to Cp mu over K. Now, looking at this equation, Prandtl number is a function of the material's physical properties because the values of the heat capacity, viscosity, and thermal conductivity are all different for fluids. Okay? And all of these parameters are also functions of temperature, and that makes the Prandtl number also a function of temperature. So in our calculations later on, it will be very important for us to determine at what temperature do we take the values of Cp, mu, and K such that we get the correct number of Prandtl number. The Prandtl number will play a very important role in our calculations later. Okay? So do not forget that Prandtl number is equal to Cp mu over K, or we can use the definition momentum diffusivity over thermal diffusivity. Next, let us now relate momentum transfer to heat transfer by convection. Convection relies on the motion of a fluid. Let's consider a fluid flowing over a flat plate in which the temperature of the solid surface is higher than that of the fluid. That is very important because that lets us assume that the transfer of heat will be from the solid surface to the flowing fluid at the top of the plate. Given here are the velocity and the temperature profile, you would see a familiar velocity profile in which the velocity at the boundary would be equal to 0. And you can also see a familiar temperature profile wherein this is Ts minus T infinity. T infinity refers to the free stream temperature of the fluid. The fluid layer directly adjacent to the boundary, of course, is not moving because of the no-slip boundary conditions. That's why its temperature must be equal to the temperature of the surface of the flat plate. And if the fluid layer directly adjacent to the boundary is not moving, therefore, there is no convection happening on that layer. We still have a very, very thin layer of conduction due to the no-slip boundary condition. So if you write our governing equations for convection and conduction, for convection we have Qy, meaning the transfer of heat is through the y direction, is equal to H times A times the difference in temperature, surface temperature minus free stream temperature of the fluid. Next, we write our Fourier's law equation for the heat transfer by conduction. That is Q sub y is equal to Ka times dt over dy. dt over dy is our temperature gradient, and we are only evaluating our heat transfer by conduction at a position y is equal to 0. So why are we specifying that our conduction is only at y is equal to 0? Again, as I have mentioned earlier, due to the no-slip boundary condition, there will be a layer of fluid adjacent to the surface boundary that is not moving. Therefore, that is the only place wherein we have conduction. We are also saying that the rate of heat transfer is constant, so the rate of heat transfer by conduction and convection should be equal. Equating these two equations, we have this form of the equation. And if we rearrange the terms such that we gather the gradients on one side and the constants on the other side, we get this equation. H over K is equal to the gradient due to conduction over the gradient due to convection. If we multiply L to both sides of the equation, we get the collection of terms HL over K is equal to the gradient due to conduction over the gradient due to convection. But now, the right-hand side of the equation will become dimensionless. Okay? Now, this collection of parameters HL over K is very important in convective heat transfer because this is what we call the Nusselt number. We define the Nusselt number as the surface thermal gradient, that is the temperature gradient due to conduction, divided by the overall thermal gradient, which is the gradient brought about by convection. If you will notice, the formula for the Nusselt number looks a lot like the BO number. The BO number is H times V over A over K, which in some instances would lead to the equation HL over K, but they are two different dimensionless numbers, okay? The BO number is defined as the ratio of the resistances due to conduction and convection. Now, since we are talking about the dimensionless Nusselt number, let us now enumerate all of the important dimensionless numbers that we will encounter for convection. This is both for natural convection and forced convection. We have the Prandtl number as discussed earlier, which is the ratio of the momentum and the thermal diffusivities. The Reynolds number, which we have discussed in momentum transfer. Nusselt number, which we have derived here. We also have the Peclet number. The Peclet number is simply the products of the Reynolds and the Prandtl number. Okay? In some instances, it is better for equations to be expressed in terms of the Peclet number. That's why we are including it here. Next, we have the Stanton number, which is the ratio between the Nusselt number and the Peclet number. Therefore, the Stanton number becomes Nusselt number over Reynolds number times Prandtl number. We also have these two dimensionless numbers for natural convection, which we will tackle on the next part of this lesson, Grashof number, GR, and Rayleigh number, or RA. The Rayleigh number is simply the product of the Grashof number and the Prandtl number. If you will notice, among all of these dimensionless numbers, only two contain the term for the heat transfer coefficients of convection H, that is the Nusselt number and the Stanton number. In the problems that we will be solving later, it will be very important for us to estimate the value of the heat transfer coefficient H. That's why we will be solving for the values of the dimensionless numbers, Nusselt and Stanton numbers. Now let's dive deeper into forced or induced convection because this will be the focus of this part of the lesson. Forced convection is simply the transfer of heat via convection that is aided by a rapid movement of the fluid. We can illustrate forced convection with this figure. You have here a high temperature object, and the heat transfer between the high temperature object and the low temperature air is enhanced by the flow that is caused by the fan. If the air here is stagnant, the rate of heat transfers would be lower, and we will be entering the realm of natural convection. The rule of thumb for forced convection is the heat transfer via convection is directly proportional to the velocity of the fluid raised to a positive integer n. At the very least, n could be positive 1, which means that the rate of heat transfer via convection is linearly proportional to the velocity of the fluid. So the faster the flow of the fluid, the higher the rates of heat transfer due to convection will be. Okay? That is our mantra for forced convection. That's why the velocity of the fluid is a very important parameter in forced convection. If you go back to our dimensionless numbers, only the Reynolds number contain the parameter velocity. So you can now imagine that we will be using relationships between the Reynolds number and the Nusselt number in this part of the lesson. Okay? Because we are relating the rate of heat transfer to velocity. And since momentum transfer plays an integral role in the rate of heat transfer via convection, we have come up with what we call analogies between momentum transfer and heat transfer. When we say analogies, there are similarities on the way on how we solve for parameters in momentum transfer and heat transfer. For this purpose, we recall the definition of the fanning friction factor. The fanning friction factor is what you are determining in fluid mechanics to determine the pressure drop in a pipe due to friction. Technically, we define the fanning friction factor as the shear stress at the wall of the conduit divided by the density multiplied by the free stream velocity squared over 2. Now, we can determine the value of the friction factor using several correlations found in our handbook. It depends if the pipe is smooth or rough. If it is rough, you can use the Churchill equation. If it is smooth, you can use the Blasius equation. Our first analogy is called the Reynolds analogy. The Reynolds analogy is simply written as the Stanton number is equal to the fanning friction factor over 2. Meaning, if we are able to solve for the fanning friction factor of the flow, we can already determine the Stanton number, which in turn can be used to determine the heat transfer coefficients by convection. Okay? But here's the catch. The Reynolds analogy is only valid if the Prandtl number of the system is equal to 1. This is a very limiting condition because not all practical systems have a Prandtl number of exactly 1. And another limitation is that the Reynolds analogy can only be used for laminar flow. For other instances wherein the Prandtl number is no longer equal to 1, we can use the what we call Chilton-Colburn analogies. The Chilton-Colburn analogy can be applied if the Prandtl number is between 0.5 and 50. And the Chilton-Colburn analogy makes use of what we call the J factors. So we have 3 J factors: the J factor for momentum transfer, the J factor for heat transfer, and the J factor for mass transfer. For momentum transfer, the J factor is equal to F over 2 or the fanning friction factor over 2. For convective heat transfer, the J factor has a value of the Stanton number multiplied by the Prandtl number raised to 2/3. So the same thing is applied here. If you can solve for the fanning friction factor and you can solve for the properties of the fluid such that you can get the Prandtl number, you can substitute all of those in the Chilton-Colburn analogy and we can solve for the heat transfer coefficients coming from the Stanton number. But the Chilton-Colburn analogy also has a limitation, and that is it can only be applied to the laminar flow of fluids as well, just like the Reynolds number. But at least the Chilton-Colburn analogy can be applied for a wider range of Prandtl numbers. If you are looking for an analogy that can be used for turbulent flow, we can use the Prandtl analogy. The Prandtl analogy is given here. It still follows the format of the previous equations in which the Stanton number is a function of the fanning friction factor and the Prandtl number. Again, you just have to look for the value of the fanning friction factor and solve for the Prandtl number. Substitute everything here and you can have the value of the Stanton number. We have another analogy called the von Karman analogy, which is a refined version of the Prandtl analogy, and the equation just got longer. Now, aside from analogies, we also have Nusselt number correlations that we can use to solve for the heat transfer coefficient of a certain system. Now, it is important to note that these Nusselt number correlations are empirical equations and are fitted from experimental data. So we can expect to see numbers here that do not have physical meanings, such as this 1.86 and the 0.14. These Nusselt number correlations are also found in your handbook, and some of them have their own criteria before you can use them. For example, this version of the Sider-Tate equation, this one, can only be used if the Reynolds number is less than 2,400 or if the flow is laminar. That is, Nusselt number is equal to 1.86 times the Peclet number multiplied by the ratio D over L raised to 1/3 times the ratio of the viscosity of the fluid at bulk temperature over the viscosity of the fluid at the wall temperature raised to 0.14. Now, you might be wondering, why is there a subscript of D in the Nusselt number? This subscript of D on the Nusselt number means that instead of your Nusselt number equation becoming HL over K, it now becomes HD over K, with the D being the internal diameter of the pipe. Okay? For turbulent conditions, that is Reynolds number greater than 10,000 and the Prandtl number ranging from 0.7 to 17,000 with the length over diameter ratio that's greater than 60, you can use these versions of the Sider-Tate's equation. We will be using this equation. Nusselt number is equal to 0.023 times Reynolds number raised to 0.8 times Prandtl number raised to 1/3 times the ratio of the viscosities raised to 0.14. Quite a lot because this is one of the simpler correlations for Nusselt number. Keep in mind that what we are discussing right now is the Nusselt number correlations for internal flow, meaning that your fluid is flowing inside of a pipe. We have other correlations. Let's say, for example, the Ditus-Boelter correlation. This Ditus-Boelter correlation looks a lot like the Sider-Tate equation. It has a form of Nusselt number is equal to 0.023 Reynolds number raised to 0.8 times Prandtl number raised to n, wherein the n has different values depending if the fluid is being heated or is being cooled. Now, if your length over diameter ratio is not greater than 60, meaning it's less than 60, you can use this Dirichlet correction factors to adjust the value of your heat transfer coefficient. Okay, let's try to solve this example. Water, initially at 30 degrees Celsius, is flowing inside a 2-inch Schedule 40 commercial steel pipe at a rate of 1.8 kilograms per second. The pipe is 5 meters long and its inner wall is maintained at 100 degrees Celsius by condensing steam on the outside. The water temperature at the outlet is measured to be 52 degrees Celsius. Determine the heat transfer coefficient and how much heat was transferred. Here we have our given to the problem. We have our pipe, 5 meters in length, and our water is flowing inside at a rate of 1.8 kilograms per second. The temperature at the entrance is 30 degrees Celsius, and its temperature at the exit is 52 degrees Celsius. The water is being heated by condensing steam on the other side of the pipe, which is set at 100 degrees Celsius. So the heat transfer in this case will be from the wall of the pipe to the water flowing inside. And you know that this is a case of heat transfer via forced convection because we are given the mass flow rate from which we can solve for the bulk velocity of the fluid. Before we can do any calculations, we first have to determine the internal diameter of a 2-inch Schedule 40 pipe as well as the physical properties of water. So you need to practice your determination of the physical properties of fluids because it will come up a lot in our discussion in convection. The internal diameter of the pipe can be seen in our handbook. That is in Chapter 10, Table 10-22, Properties of Steel Pipe. If we take a look at 2-inch Schedule 40, it is here, 2-inch Schedule 40. The internal diameter is 2.067 inches. And we just have to convert that to meters. The internal diameter of our pipe is now 0.0525 meters. We converted it from the original value of 2.067 inches. The internal diameter of the pipe here is very important because it lets us to determine the velocity of the flow inside of the pipe. And that will come from the mass flow rate. If you will remember, we defined the mass flow rate as being equal to rho, or the density of the fluid, multiplied by the velocity, multiplied by the cross-sectional area of the pipe. And for that, we need the density of water. So let's look for the density of water. And while we are at it, let's look for the viscosity, thermal conductivity, and Cp of water. The question is, at what temperature do we take these physical properties of water? Do we take it at 30 degrees Celsius, which is the entrance temperature? Or do we take it at 52 degrees Celsius, which is the exit temperature? Or do we take it at 100 degrees Celsius, which is the wall temperature? For problems on forced convection, always remember that we are evaluating the properties at the bulk temperature. The bulk temperature, T sub B, is simply the average of the entrance and exit temperature. In our case, that will be the average between 30 degrees Celsius and 52 degrees Celsius. That would be 30 plus 52 over 2. We have 41 degrees Celsius. Converting it to Kelvin, we have 41 plus 273.15. That is 314.15 Kelvin. It is this value of the bulk temperature which we will use to evaluate all of the physical properties of water. Okay? If you evaluated the properties at 30 degrees Celsius, you would be wrong because those properties would change once the water starts to heat up. Always remember to use the bulk temperature. At the bulk temperature of 314.15 Kelvin, the density of water is 992.08 kilograms per cubic meter. The viscosity at the same temperature is 6.59 times 10 to the negative 4 Pascal seconds. The thermal conductivity is 0.627 watts per meter per Kelvin. And the heat capacity of water is 4,177 joules per kilogram per Kelvin. Notice that I used all of the standard units in the SI system so that we will not have any problems when computing the dimensionless numbers later. Okay, these four physical properties, density, viscosity, thermal conductivity, and heat capacity, will almost always be used in your calculations in convective heat transfer. So please practice obtaining these values from your handbook. Let's go back to our mass flow rate equation. From this equation, we can solve for the velocity as the mass flow rate over density over the cross-sectional area. Just a side note, The cross-sectional area in this case is the area of a circle. That is pi over 4 times internal diameter squared. Okay? It is very important to make a distinction that this is a cross-sectional area because we will be using another type of area, which is the surface area, later in our calculation of heat transfer. Solving for velocity, we have 1.8 kilograms per second times density of 992.08 kilograms per cubic meter times the cross-sectional area pi over 4 times diameter 0.0525 squared. The velocity of our fluid is 0.838 meters per second. This value of the velocity will be important in our calculation of the Reynolds number. Speaking of Reynolds number, once you have obtained all of the parameters for the fluid as well as the velocity of the flow, that is the first dimensionless number that we have to calculate because we need to determine if the flow is laminar or turbulent before we can select our correlation for the Nusselt or Stanton number. Okay? Solving for the Reynolds number, that is d u rho over mu. Substituting, diameter is 0.0525, velocity is 0.838, density is 992.08, viscosity is 6.59 times 10 raised to negative 4. Our Reynolds number is 66,232. Therefore, we say that the flow is turbulent. Now that we know that the flow is turbulent, we can now select our correlation in order to determine the Nusselt number, and in turn will determine our heat transfer coefficient. By the way, the unknown in this problem is the value of the heat transfer coefficient H as well as the rate of heat transfer Q. Okay, let's go back to our lesson and take a look at the available correlations that we can use. For internal flow, we can use this Sider-Tate equation, the second version, this one, which is intended for turbulent flow. We know that our Reynolds number is greater than 10,000, but we first have to solve for our Prandtl number to confirm that it is between 0.7 and 17,000. So this is one of our equations, the Sider-Tate's equation. The next equation that we can use is the Ditus-Boelter equation. This is the form of the equation. We just have to verify if our Prandtl number is between 0.7 and 100 and our length over diameter ratio is greater than 60. The value of n in our case is 0.4 because our fluid is being heated because the wall temperature of the pipe is higher than the bulk temperature of the water. That's it for the correlations that we can use. So the Ditus-Boelter and the Sider-Tate equation. But remember that we can always use the analogies between momentum and heat transfer. We can use the von Karman analogy. We just have to solve for the value of the fanning friction factor. And we can also use the Prandtl analogy because the Prandtl and von Karman analogies are both suited for turbulent flow. So we will be testing 4 different equations to determine the value of the heat transfer coefficient, and we will see if there are differences between those equations. Let's start by determining the fanning friction factor to be used in the Prandtl and von Karman analogies. For the fanning friction factor, we have to use the Churchill equation, which is found in chapter 6. That is equation 6-39. So this Churchill equation only needs the value of the Reynolds number, which we have already solved, and the relative roughness epsilon over d. For commercial steel pipe, we are given values of roughness here. Commercial steel, the surface roughness is 0.0457 millimeters. Okay? Let's go back to the drawing board. Our Churchill equation is 1 over square root of f, that would be our unknown, is equal to negative 4 times the logarithm of 0.27 times the surface roughness 0.0457 times 10 raised to negative 3 divided by the diameter of the pipe 0.0525 plus the ratio 7 over Reynolds number 66232 raised to 0.9. We can use the shift solve function to solve for the value of the fanning friction factor. We get a value of 5.73 times 10 raised to negative 3. The fanning friction factor is dimensionless. Okay? Now, what's left is for us to solve for the Prandtl number, and then we will be set to determine the heat transfer coefficients. Prandtl number, Cp mu over K. We already have the properties of water. So that will be 4177 times viscosity, 6.59 times 10 raised to negative 4 divided by thermal conductivity, 0.627 watts per meter per Kelvin. Our Prandtl number is 4.39. So we now know that we can use the Ditus-Boelter and the Sider-Tate equation because our Prandtl number is within their requirements. The final parameter that we have to compute is the L over D ratio, which should be greater than or equal to 60 for us to be able to use the Ditus-Boelter and the Sider-Tate's equations. Our L over D ratio is 5 over 0.0525. That is 95, which is greater than 60. Therefore, we can use those equations. Since we will be using 4 different equations to determine the value of the heat transfer coefficient, it would be better if we can compare that with an actual value. We will do that later. Listing our options, we have the Sider-Tate, the Ditus-Boelter, the von Karman analogy, and the Prandtl analogy. We will be solving for the Nusselt number and the Stanton number, and subsequently, we will be determining the heat transfer coefficients. Let's start with the Sider-Tate's equation. This is the form of the Sider-Tate equation. Now, notice in this equation that we need to find the value of the viscosity of the fluid at the wall temperature, that is mu sub W. So, mu sub W is simply the viscosity of water at 100 degrees Celsius. And upon calculations, that is 2.79 times 10 raised to negative 4 Pascal second. Now we can substitute everything and we can determine the Nusselt number. So we have 0.023 times the Reynolds number, 66232, raised to 0.8 times the Prandtl number, 4.39, raised to 1/3, times the ratio viscosity at the bulk temperature, that is 6.59 times 10 raised to negative 4 divided by viscosity at the wall temperature, 2.79 times 10 raised to negative 4, and we raise the ratio to 0.14. We get a value of the Nusselt number as 305.5. That is from the Sider-Tate equation. Now let's go to the Ditus-Boelter equation. The Ditus-Boelter equation is Nusselt number is equal to 0.023, Reynolds number raised to 0.8 times Prandtl number raised to 0.4 because our fluid is being heated. If we substitute, that is 0.023 times Reynolds number 66232 raised to 0.8 times Prandtl number 4.39 raised to 0.4. Our Nusselt number from the Ditus-Boelter equation is 298.93. Next is for the von Karman and the Prandtl analogy. For those two analogies, we will not be solving for the Nusselt number. We will be solving for the Stanton number. The von Karman analogy is Stanton number is equal to fanning friction factor over 2 all over 1 plus 5 times square root of fanning friction factor over 2 times Prandtl minus 1 plus ln of 1 plus 5 over 6 Prandtl minus 1. Let's solve for the Stanton number. That is fanning friction factor over 2, 5.73 times 10 raised to negative 3 divided by 1 plus 5 times the square root of the friction factor, 5.73 times 10 raised to negative 3 over 2. Prandtl number, 4.39 minus 1 plus ln of 1 plus 5 over 6 times Prandtl number minus 1, 4.39 minus 1. Our Stanton number is 3.62 times 10 raised to negative 3. And finally, the Prandtl analogy. That is, Stanton number is equal to friction factor over 2 over 1 plus 5 square root of friction factor over 2 times Prandtl minus 1. Substituting, we have 5.73 times 10 raised to negative 3 divided by 2 over 1 plus 5 times the square root of 5.73 times 10 raised to negative 3 over 2 times Prandtl number 4.39 minus 1. Our Stanton number is 1.92 times 10 raised to negative 3. So those are our dimensionless numbers coming from 4 different equations. Now, from each of these equations, we can solve for a value of the heat transfer coefficient. How do we solve for the heat transfer coefficient? Remember the definition of the Nusselt number and the Stanton number. The Nusselt number is hd over k, while the Stanton number is h over u rho cp. Rearranging, from Nusselt number, our heat transfer coefficient is equal to Nusselt number times k over d. And coming from the Stanton number, our heat transfer coefficient is equal to Stanton times velocity times density times Cp. Now we can compute for the heat transfer coefficients. Let's start with the Nusselt number from the Sider-Tate's equation. Our heat transfer coefficient is 305.5 times thermal conductivity 0.627 divided by the diameter of the pipe, which is 0.0525. Our first heat transfer coefficient is 3648.54. Next, coming from the Ditus-Boelter equation, we have 298.93 times 0.627 divided by 0.0525. We have 3570.08. By the way, the units of the heat transfer coefficient is watts per square meter per Kelvin in standard SI units. Next, for the Stanton numbers, that would be 3.62 times 10 raised to negative 3 times velocity 0.838 times density 992.08 times heat capacity 4177. We have 12,570.82. And lastly, from the Prandtl analogy, we have 1.92 times 10 raised to negative 3 times velocity 0.838 times density 992.08 times Cp 4177. We have 6,667.40. Now, we have obtained 4 different values of the heat transfer coefficient. The question is, which among this is the correct value? Now, we can check our values using the overall heat equation. If you will remember, our convection equation is Q is equal to HA times delta T. The delta T in our equation, or the driving force, would be the temperature of the wall, T sub W, minus the bulk temperature of the water. Remember, the bulk temperature is the average temperature of the water while it's staying inside of the pipe. Now, since we know the inlet and outlet temperatures of water, we can also use the equation Q is equal to mCp delta T to determine the actual heat that is transferred to the water. So we write Q is equal to mass flow rate times Cp times delta T. In this case, delta T is the change in temperature of water. This now becomes T2 minus T1. If you will notice, we have used 2 different values of delta T. The first delta T is the driving force of the heat transfer. The second delta T is the change in temperature of the water. Do not interchange those two. Okay? Now, since the rate of heat transfer is equal, we can equate these 2 equations. We get HA times TW minus TB is equal to M Cp times T2 minus T1. You can see from this equation that we can directly solve for the value of the heat transfer coefficient, which is mass flow rate Cp times T2 minus T1 all over area times TW minus TB. Now, the question is, what area are we pertaining in this instance? This area came from our equation of the overall heat transfer, Q is equal to HA delta T. If it comes from our overall heat transfer equation, that area is the surface area of transfer. And based from our system, the surface area of transfer is the inner surface area of the cylinder, that is pi dl. Let's solve for the value of the heat transfer coefficient. Mass flow rate is 1.8 kilograms per second. Cp is 4177 times T2 minus T1, that is 52 minus 30. No need to convert them to Kelvin because delta T in degrees Celsius is the same as the delta T in Kelvin. Okay? Divided by area, that is pi times diameter 0.0525 times the length of the pipe 5 meters times temperature difference, wall temperature minus bulk temperature, that is 100 minus 41 degrees Celsius. The actual value of our heat transfer coefficient is 3,400 watts per meter squared per Kelvin. Now, in this instance, we were able to solve for the actual value of the heat transfer coefficient because we are given the outlet temperature of the water. In some instances, you will not be given the outlet temperature of the water. That's why you have to rely on correlations to determine the heat transfer coefficients. And based on our choice of the correlations, both the Sider-Tate's and Ditus-Boelter equations were fairly close to our actual heat transfer coefficients. Okay? While the von Karman and the Prandtl analogies were very far from our values. That's because the von Karman and Prandtl analogies were theoretical in nature, while the Sider-Tate and Ditus-Boelter equations are empirical in nature. For our case here, empirical equations which are based on experimental data are much better in giving a reasonable value of the heat transfer coefficient. So from now on, we will only be using empirical equations or correlations to determine the value of the heat transfer coefficient. In this problem, I have shown you the step-by-step process on how we were able to solve for the heat transfer coefficient. To recap, you first have to complete your given. You look for the values of the physical properties of the fluid, that is, density, viscosity, thermal conductivity, and heat capacity. And after that, you simply solve for the Reynolds number and the Prandtl number, and then substitute those in our correlation for the Nusselt number. And from that, you can solve for the heat transfer coefficient. Let's answer the second part of the question, which is the total heat transfer Q. If we are going to use our heat transfer coefficient coming from the Sider-Tate equation, we write Q is equal to HA times wall temperature minus bulk temperature. We substitute our solved values. That is 3,648.54 times area, that is pi dl, pi times 0.0525 times 5 times the driving force, wall temperature 100 degrees Celsius minus the bulk temperature 41 degrees Celsius. Our total rate of heat transfer is 177.5 kilowatts. That is how we solve problems involving forced convection. Let's go back to the slides. Let's now discuss other Nusselt number correlations for external flow. In our previous example, the water is flowing inside of the pipe, but in some cases, the fluid is flowing on the outside of the conduits. Okay? For our first correlation here, this is applicable for cross flow through a single cylinder. When we say cross flow, that means that the direction of flow of fluid is perpendicular to the cylinder. Okay? We use the Churchill-Bernstein equation, but the product of the Reynolds number and the Prandtl number, or the Peclet number, must be greater than 0.4, and the fluid properties are evaluated at the film temperature. The film temperature is different from the bulk temperature. Okay? The film temperature is the average between the bulk temperature and the wall temperature. Just to recap, the bulk temperature is the average between the inlets and outlet temperatures of the fluid, and the film temperature is the average between the bulk temperature and the wall temperature. This is your Churchill-Bernstein equation. Next, we have for flow past an isothermal sphere, we have the Whittaker equation. We can use the Whittaker equation provided that your Prandtl number is between 0.7 and 380, and the Reynolds number is between 3.5 and 8 times 10 raised to 4. And the ratio of the viscosity of the fluid at the free stream temperature over the viscosity of the fluid at the surface temperature is between 1 and 3.2, and we evaluate the properties at the free stream temperature. You have to be careful at the specifications of your correlations because some of them would call for the use of the bulk temperature, some would call for the use of the film temperature, and in this case, we use the free stream temperature. Here is your Whittaker equation. We also have, for laminar flow on a flat surface, we use the Churchill-Ozo equation. For flat surfaces, our threshold for the Reynolds number of laminar flow is not 2,100 like in the flow inside pipes, okay? So for the Churchill-Ozo equation, you can use it if the Reynolds number is less than 5 times 10 raised to 5 and the Peclet number is greater than 100. And you evaluate the fluid properties at the film temperature. This is the Churchill-Ozo equation. For turbulent flow on a flat surface, we use the Mills equation, provided that your Reynolds number is greater than the critical Reynolds number. The critical Reynolds number is given here at the top, that is 5 times 10 raised to 5, and it is less than 3 times 10 raised to 7. Your Prandtl number must be between 0.7 and 400, and your fluid properties have to be evaluated at the film temperature. This is the Mills equation. We also have here Nusselt number correlations for the flow past a bank of tubes. Now, I will be providing a separate video on this because this is a special case of external flow, okay? We will go back to these equations in a separate video. And finally, here are some practice problems that you can solve on your own. You need to take note that in these problems, the exit temperature of the fluid is not given. So you would first need to assume an initial value of the exit temperature, solve the problem, and then determine the exit temperature through our equation Q is equal to mc delta T is equal to HA delta T. These problems are iterative in nature. I will be posting separate solutions to these practice problems, so please watch out for that. And that's the end of this lesson for forced conduction. Please keep a watch out for the second part of this lesson for natural convection. Keep practicing solving for the physical properties of substances because we will be using those a lot. Also keep practicing solving for the values of the dimensionless numbers. Thank you for listening and keep safe.